Hope everybody's back from break. So before break, we were talking about the registers file, and now we're going to talk about main memory, semiconductor main memory. We have semiconductor memory cell, which has three different key features. It has first two stable states, which is represented by 0 and 1. It can be written to at least once, which means it can be written to allow it to be set, and it can be lead to detect the state. So these are the main three properties of a semiconductor memory. It has two different stable states represented by 0 and 1. It can be written to at least once, and it can be used to detect the state. Now we have memory cell operations example. Now on the screen here, we have a picture on the screen. On the left side, it is a write operation. What it does do, it is as first to select the line to be activated. That means that this cell is selected among many memory cells, and the control here indicates that it is a write operation. This is a write operation. That means that the data in line has to carry the value. That means 0 or 1, and it has to be stored. It has to be stored in. That is why we have a data in. We have to store the value which is selected to be in this cell. The main memory cell then latches the data internally. On the other side, we have the read operation, and the line here, as you can see, is selected active to be a read operation, and this cell is selected to be a read operation. So the cell needs to output the stored value onto what we call a sense. So it has to output this data that we have stored in write operation in sense. So the sense has to be amplified to read the small voltage from the cell. So this is picture on the screen normally depicts a basic memory cell, and it has also to demonstrate how it operates during write and read operations. Now, we're going to talk about different types of memory, starting with the random access memory, RAM, which stands for random access memory. RAM allows easy and rapid reading, as well as writing of the data using electrical signals. It is a volatile memory. Volatile memory, that means the data is lost when the power is interrupted. So this is a volatile memory. As I said before, a volatile memory means that a memory remained with the data as long as it has the power supplied. When the power is interrupted, that means the data will be lost. So this is what we call a volatile memory. So RAM requires a constant power supply for operation. We have two types of RAM, DRAM, dynamic RAM, and static RAM. Now we're going to talk a little about the difference between DRAM and SRAM. Now, the DRAM stores data as charge on capacitors, binary 1 or 0. So these capacitors are naturally discharged. That means they require periodic refreshing to retain data. So if the data is stored on DRAM, it has to be refreshed to retain data. So which means the dynamic weight there in the DRAM indicate the need for charge refresh due to the leakage. So we have the structure of the DRAM here. We have the bit line 0, and we have the address line. The transistor here that we have in the DRAM structure is there to act as a switch, which means when it's closed, there is a current that flows, and when it's open, there is no current that flows. We have the ground and we have the storage capacitors. So we have the DRAM, which store the data as charge on capacitors 0 and 1. Now, what is a static lamp? A static lamp, on the other hand, it is a digital device which uses the same logic element as the processor. So binary values are stored using flip-flops, logic gate configuration. For the DRAM, we have seen that those data are stored as charge on capacitors. That's why we need to refresh it to retain data. For SRAM, we see that it does have to store the data using flip-flops, logic gate configuration, which means that a static lamp we hold its data as long as the power is supplied. You don't need, it doesn't require to refresh it again and again because it does store the data using flip-flop logic gate configuration. Now, this picture on the screen depicts what we call a SRAM cell. This is a 6-transistor SRAM, which is the standard for the static lamp. And we're going to break these into more details. We have T1, transistor 1, T2, and T3, and T4. These are MOSFET forming what we call close-capped inverters. We have T1 and T3, T1 and T3. These are left inverters, and we have T2 and T4, which are the right inverters. So this is a static lamp cell with 6 transistors. As we have seen, the static lamp store the data using flip-flop logic gate configuration. We have these 6 transistors, which are MOSFET, to form 2 closed-coupled inverters. We have T1 and T3, transistor 1 and transistor 3, which are there to form the left inverter. And we have T2 and T4, which are there, T2 and T4, which are there to form the right inverter. To summarize, these 2 types of memory, lamp memory, they are all volatile, which means they store data when the power is supplied. And when it comes to the size, the static lamp is larger if you compare to the dynamic lamp, and the static lamp is more complex. For the density, the static lamp is less dense. That means we have fewer cells per unit area. For DRAM, we have more dense. It is more dense. That means it have more cells per unit area. So when it comes to the cost, the SRAM is a bit expensive if you compare with the DRAM. For static lamp, no need of refresh because it does store data using flip-flops. Logic gate configurations. And for DRAM, it has to be refreshed to retain data. For speed, SRAM is faster and the DRAM is slower. Now, what are the difference when it comes to usage? The DRAM is used in the main memory, and the static lamp is used mainly in cache memory. We have seen what is a cache memory, which is there to hold most frequently used data and instruction, and it has to be faster to minimize or to improve the computer performance. So we need the SRAM to be used in cache memory because the SRAM is faster. All right, now the second type of memory that we're going to learn is the read-only memory, ROM. So the read-only memory contains a permanent pattern of data that cannot be changed. So it is a non-volatile memory, which means no power is needed to maintain its data. Data can be read or, but it cannot be written to the read-only memory. There are many applications of ROM memory in programming or in system programs or in function tables. Now, another type of ROM is PROM, programmable programmable ROM. This is programmable read-only memory. This means that this is like the ROM that we just learned. It is a non-volatile memory. It can only be written to once. So what does this mean? Writing to this type of memory is done electrically and can be performed by the supplier or the customer after chip fabrication. So this EPROM, this programmable ROM, they are more flexible memory and they are convenient. We have also EPROM. EPROM also is like the EPROM that we just learned. It is read and written electrically like the PROM that we just saw previously. So before writing to this type of memory, also storage cells need to be erased to initially have a space for the content. So we have to use UV radiation, and the EPROM can be changed multiple times and retain data indefinitely. So this is a non-volatile memory. Now, how about the cost? How about the cost of this type of memory? This type of memory, EPROM, is a bit expensive if you compare with the previous one, PROM, but it does offers multiple updates. It does offers advantage of having multiple updates. So this means the EPROM is also a read-only memory, but it does provide more advantages when it comes to updates. The next type of memory is the flash memory. The flash memory is named for the speed. It has a speed which can be reprogrammed. So which means that the speed of the flash memory can be reprogrammed, and this type of memory was introduced in 1980s. It is like the intermediate memory between EPROM and EEPROM in both cost and functionalities. So this entire flash memory can be erased in 1 or few seconds. It is much faster than the EPROM that we just learned in the previous slide. So flash memory does not support byte level enlarger. That means that it does not supposed to be erased byte by byte. So chip logic. We have semiconductor memory, which comes in packaged chips. That means that each contains an array of memory cells. So we have each memory which comes in a package. Each package contains an array of memory cells where we have to select, when the CPU we have to select 1 word out of millions of words. And these are the trade-off between the speed These are the trends between memory speed, memory size, and the density, memory density. So when we talk about memory density, memory size, and the memory speed, we cannot also ignore the cost of the memory. That means we need speed for the memory, size also, density as well as then see how much it's gonna cost us. So what is the cost for this memory with these following features? This much speed, this much size, this much density. So we need also to talk about the cost for the memory. So a key issue here is the number of bits that can be read from the memory or written to the memory. So how many bits can be read from the memory at one time, or how many bits can be written to the memory at one time? This is also a key design in memory, semiconductor memory. We need to know what are the total number of bits that can be written to the memory at one time, and what is the total number of bits that can be read from the memory at one time. So one organization has the physical arrangement of the cell to match the logic arrangement perceived by the processor. So the array is to organize into a word of this number of bits each. Hello? Now, the array needs to be arranged in words. This means the last line means that the array, the memory array, needs to be arranged into W words. We have number of words. Number 1, word 1. Number 2, word 2. Then dot dot, like this one, we have how many words. How many words do we have for this memory? We have 1024. So this is 1024 words. Now, the array needs to be arranged in different words from 1 till the last word. And each word needs to have a number of bits. How many bits? We have seen, for example, that this one has a number of 1024 words, and each word is 2 bytes. That means each word is 16 bits, right? So we need to have 16 bits in each word. 1, 2, 16, all 2 bytes. This also should be 1, 2, till 16 bits. Bits, all 2 bytes. And this also should be 16 bits, all 2 bytes. So this means that the memory cell needs to be arranged in array, and each array is organized into words. How many words? Depending on the number of bits on data bus, we found the total number of words, and each word is how many bits or how many bytes. We needed to take the total number of bits in data bus. Then we found the total number of bytes per each word, or we can use this number of bytes, this number of bits to determine the number of bytes in each word. So this is how our array needs to be arranged. So when it comes to read data from the memory, our CPU will select one word at a time out of millions of words. So we're going to talk about bit line select in our next lectures to know how the memory array is arranged and how does our our CPU try to read the data from the memory or try to write data to the memory. This is something that we're going to discuss later on in our course. Now, to summarize, we have memory types on the screen. We have the random access memory, which is a read-write memory. It is a volatile memory. We have read-only memory. We have the different types of read-only memory. Then we have the flash memory as well, which is a non-volatile memory. So we just talked about memory levels, different types of memory. Now we're going to talk about a little bit about the memory organization. On the screen, we have a typical 16 megabyte DRAM, which is 4M times 4. This means these diagrams on the screen shows the internal organization of the DRAM chip. Specifically, is a 16 megabyte DRAM. That means we have this arranged in 4 times 4. The memory size is 16 megabytes arranged in 4 million words. Each word is 4 bits. Now, what does this mean? It means that our 16 megabyte DRAM has 4 million of words, and each word has 4 bits. As we can see here, we have a 16 megabyte DRAM. That means it has 4 million of words, and each word is 4 bits. We have the colon address strobe and the low address strobe. For the colon address strobe is a signal to the DRAM to latch the colon address, and for the low address strobe, it is a signal to the DRAM to latch the low address for the memory. So, and then we have a timing and control signal. So for this 16 megabyte DRAM, it has 4 million words, which arranged in which one has 4 bits. Each one has 4 bits. We have here the colon address strobe, which is then after each low is selected, it has to be selected via the low address strobe. Then the colon address strobe will select the colon for a specific memory cell. So here we have the low address strobe also, which is there to prepare the low that has to be selected. So this means that, in summary, this diagram on the screen, they show an internal organization of a type of DRAM chip, which specify a 16-bit megabit DRAM arranged into 4 million words, and each word is a 4-bit. That means we have each word which is 4 bits, and we have address line, which are enough to access the 4 million words. So at each time, the processor will select one word out of millions of words. We have address line, as is depicted by this picture. We have different address line, A0 till A10, and we have the row address buffer and the colon address buffer. So for low decoder, we have the low decoder as well as the multiplexer. We have to learn about how the CPU selects one word out of these million of words later on this course. And you see, here we have refresh circuit. This means you see it's a kind of DRAM that needs to be refreshed to retain the data. Now, what does it do when it comes to multiplexing, low colon multiplexing? So the DRAM has to use a low and the colon address multiplexing to reduce the number of the address pins. For the low address, it has to be sent first, then it has to be latched into what we call low address buffer as depicted by the previous picture. Then it has to be decoded by the low decoder. So when it comes to the colon address, it has to be sent next after the low address. That means the microprocessor needed to select first the low address. It has to select one word out of million of words. Then the colon address will be sent after, and it has to be latched into what we call colon address buffer to be decoded by colon decoder. So this allows to have 2 out of 2 to the power of n times 2 to the power of m array to be addressed with fewer pins. So this will minimize what we call the complexity of our multiplexer in our 16 megabyte DRAM that we do have here on the screen. Now, we have seen that each memory comes in a package, so we need to talk about chip packaging. It has address pins. For 1,000,000 words, we have 22 pins. That is from A0 up to A19, which are needed to specify the address. We have the data pins. That means we have 8 lines from D0 to D7. And this is for leading data. The power also needs to be supplied. We have also the ground pin, the VGSS pin for ground. We have also the pin for chip enable. This is there to indicate that if the address is valid for the chip, it has to be activated by the logic, which is connected to higher order address bit and above. That means above the pin 19. Then we have program voltage, which is there as a supplied during the programming or during the write operations. Now we have an 8 megabit EEPROM. As we just talked in the previous slide, you see it has a number of address pin and a number of the data pin. Address pin is for specify the address of the operation, and for data pin is for leading the data. We have a number of data pin. You have D0, D1, D2, and so on and so forth. And we have a total number of a big number of address pins. These address pins are very important to specify the address. Then we have also the VCC. We have also the VPP. So we have also the chip enable for this EEPROM. The chip enable, which is used to indicate if the address is valid for this chip or not. So this is a simple example of a 80-bit megabyte EEPROM. So now we're going to talk about module organization. We have to talk about module organization. If a RAM chip contains 1 bit per word, that means that the number of chips that needed equals to the number of bits per word. So this is very important. If we have a RAM chip and this RAM chip has only 1 bit per word, that means that the total number of chips that are needed is equal to the total number of bits per word. We have a simple example. A memory module with a 256 kilobytes each is 8-bit word. That means that we have 18-bit address, which is required to address this 256 kilobyte word. The address is then supplied externally from a bus, for example. So the memory module is then organized with 8 chips. 8 chips, each one is 256 kilobytes times 1 bit. That means each chip has to handle the input and output of 1 bit. So this means that it has to deal with this input and output, but the input and output only need to be 1 bit, as it is specified by this memory module organization. So this is just a simple 256 kilobyte memory organization. We have the memory address MBR. If you still remember, we talked about the memory address, which is there to hold. It is there to hold the address. And we have the memory buffer register. The memory buffer register acts as a buffer between the microprocessor and the memory. So we have the memory size here, which is 256 kilobytes. 256 kilobytes equals to how many bytes? That means 256 times 1024 bytes. We have got this number of bytes. And when it comes to the organization, as depicted by this picture on the screen, each chip stores 512 words. Each word is 512 bits. So if you are tasked to ask to calculate the number of bits per chip, but that means that you need to take the number of words in chip, that is 512 words, and each word is 512 bits, then the number of bits in this chip is 512 times 512. Then you're gonna get the number of bits in this specific chip. Now, memory access time. For memory, we talked about the size, we talked about the speed, we talked about the density, we talked about the cost. Now, we needed to understand what is a memory access time and why it is very important. The memory access time is the total time required by the CPU to read or to write data from or to the memory. And here we have a read access time or a write access time. For read access time, that is the total time between issuing a read request and the moment the request data becomes available to the CPU. So this is what we call read access time. We have also write access time. This is there to measure how long does it take to store data at a given memory location. So write access time. How long does it take to store data at a specific memory location? We also needed to talk about bandwidth. Bandwidth, which is a total amount of data that are being transmitted per a specific time unit. So how much data can be transmitted, can be transferred in this amount of time. How many bits can be transmitted per second? This is very important. So memory access time, read access time, write access time, also understand what is the bandwidth. Now, memory interleaving. So memory can be organized in a single bank. That means one memory access can be happened at one time. So that means that, for example, in this picture on the top, we have access pattern without interleaving. That means we have to start accessing then wait for accessing D2. Because these two memory are arranged, are organized as a single bank. So we need first to get access to the D1, then wait until finish accessing the D1 so that you get access to the D2. So it is organized as a single bank, which is very difficult for the CPU to fetch data. This will involve a long waiting time for the CPU to get access to the D2, because it has first to get access to D1, then wait to access D2. There is a long wait time. So to solve this issue, we need to arrange, to organize the memory into different banks. For example, here in this case we have 4 different banks. Then the memory is divided in 4 different banks: bank 0, bank 1, bank 2, and bank 3, and so on and so forth. So which means each bank can be accessed in parallel. That means the CPU can try to get access to the bank 0. Then while accessing bank 0, it can also try to access the bank 1, bank 2, and so on and so forth. So this is going to minimize the waiting time. This will improve the throughput. So now understand, when there is no memory interleaving, that means the memory is arranged in a single bank, and one memory access can happen at one time. So when we have the memory access with interleaving, that means we have the memory divided into different banks. That means that we can get access to different memory banks at the same time, which can improve the throughput. So any question? Any question? Today we talked about memory system, memory levels, memory types, memory organization. Questions about today's class? No questions? Okay, a simple exercise to do. We have a memory with 11 bits in address bus and a data bus of 80 bits. How many words are in memory? How many bytes per word? Total number in bytes and bits. How many? You have 5 minutes to complete this. This is number 6. Write down your name, student ID, quiz number 6. Hey, be quiet. Quiz number 6. We have this question to be solved in 5 minutes. We have 5 minutes left. that's it for today's class. I will see you next time.